Good afternoon, everyone, and welcome to a continuation of our NARUC-WEEB Carbon Capture Utilization and Storage virtual workshop, stretching over 6 weeks. Today's topic is breaking it down, carbon capture utilization and storage technologies, and we are excited to be joined by three wonderful speakers. We will get started momentarily. Just wanted to do a quick review about the GoToWebinar platform. You should have a control panel, and in that control panel at any time, you're welcome to type in a question in the questions box, and we will be happy to incorporate and answer those. Or you can use the raise hands feature next to your name in the control panel, and we can unmute you when we get to the question session. If you have trouble at all with anything, please just type in the questions box, and we will do what we need to help you. I'm now going to turn this over to Kip Connington to introduce our speakers for today.
Thank you very much. So I am Kip Connington with the School of Energy Resources at the University of Wyoming. And we thank you all very much for participating in this webinar, and we hope you are all safe and healthy in these challenging times. As indicated, this is the second of a 6-part webinar series. This webinar is entitled Breaking It Down, Carbon Capture, Utilization, and Storage Technologies. It's my privilege to introduce the three panelists. First up is Dr. Holly Krutka, the Executive Director of the School of Energy Resources at the University of Wyoming. Dr. Krutka, her background is in chemical engineering and came to the University of Wyoming after a distinguished career in the energy industry, including with a utility. Our second speaker will be Jason Baker. Jason Baker is the Deputy Director of the Wyoming Energy Authority. He is also the managing director of the Integrated Test Center in Gillette, Wyoming, which is a CCUS test facility. Our third speaker will be Scott Quillinan. Scott Quillinan is the Director of Research and Outreach at the School of Energy Resources at the University of Wyoming, and he is also the Director of the School of Energy Resources Center for Economic Geology Research. So with that, Dr. Krutka, I am handing the baton off to you.
Thanks so much. Can you hear me? Okay.
Yes, we can.
You're good.
Okay. Just making sure. Okay, so thanks for bringing up my slides. Good morning, everyone. And good morning to the participants of this webinar. Really great to be with you today. And thank you to the organizers for inviting me to speak. It's very much an honor to be here. So please move to slide 2. So I am the Executive Director, as Kip said, of the School of Energy Resources at the University of Wyoming. We're very much focused on energy technologies that further the University of Wyoming's land grant mission. So the School of Energy Resources, or SER's mission, is energy-driven economic development for the state of Wyoming. And we really believe that carbon capture, use, and storage fits squarely in that mission. Today, you'll also hear from Scott, as Kip said. He's the director also for the Center of Economic Geology Research, and he's leading our Wyoming CarbonSAFE project. So I'll talk about the capture side, and I think Jason and Scott can follow up with what to do with that CO2. So moving to the next slide, please. And before I go through the technology details, I think it's really important to dispel a couple persistent myths around carbon capture and the suite of technologies that make up carbon capture, use, and storage. The first is that CCUS is something that can only be applied to the power sector. It is an emission mitigation technology that can be applied to power plant, cement and concrete production, steel production, ethanol production, natural gas reforming and natural gas production, hydrogen production, and even CO2 can be removed from the air, and actually much more. So every CCUS plant that gets built in the electric sector is driving innovation and learning by doing that will lead to cost reductions that are going to help not just the electric sector, but ultimately benefit a wide array of industries. And I also want to dispel the myth that CO2 capture is limited to 90% capture. Simply unfounded. It's not based on science. So please understand we're talking about a flexible suite of technologies that can capture nearly all the CO2 from a point source or far less, depending on what the project needs are. So go to the next slide, please. So I want to walk through the technologies in the pipeline, technology development pipeline, and those that are already ready for commercial scale deployment in the next few slides. So the largest and most advanced post-combustion CO2 capture systems are based on a suite of technologies that use aqueous amines. So that the aqueous just means it's in water, and the amine is just a class of chemicals that reacts with the CO2. So on this slide, on the right-hand side of this slide, you see a conventional CO2 capture system based on aqueous amines. So you can see two different tall vessels on this slide and in this diagram. And what those are, the one on the left is an absorber, and the one on the right is a regenerator. And so what happens in this system is this combination of these two units is used to do this, is basically the main focus of the CO2 capture system. So this is a system that's used in lots of different industries to strip acid gases, and that's essentially what's happening here with CO2 capture. In general, this process is pretty similar to what happens for SO2 scrubbing at coal-fired power plants, except one major difference. In this case, the reactant, the amine, is used over and over and over, and that's why there's two vessels. So what happens here is the vessel on the right is, like I said, the absorber, and what happens is the liquid starts at the top and moves down through the vessel. And at the same time, the flue gas from the power plant is going up through the vessel. And this gas from the power plant and the liquid from the CO2 capture systems are mixing really efficiently. And what happens during that mixing is that the CO2 goes from being in the gas to reacting with the liquid. And so by the time the gas gets to the top, let's just take a coal-fired power plant, for example. When it enters the system, or this absorber, it's maybe about 12% CO2. When it gets to the top, if you have 90% CO2 capture, it's about 1.2% CO2. Whereas the liquid is gaining CO2 as it's moving down the absorber. So then at the bottom of the absorber, the liquid can't really hold any more CO2, so it's moved over to the regenerator and it's heated up. And this liquid can't hold as much CO2 at high temperature, so it lets go of that CO2. And then you have a purified stream of CO2, and then it can be used in it can be used for enhanced oil recovery. That's the major use for CO2 today. Also, it could be used for the types of processes Jason will talk about, or maybe something else. And it could also be stored in geological storage. So that's the general idea behind CO2 capture. It's the whole process is based simply about taking this diluted stream and making it a pure stream. So if you can go to the next slide, please. So we do have one commercial scale post-combustion CO2 capture project working in the it's been built and it has been operating in the United States, and that is the Petra project. And the technology provider is Mitsubishi Heavy Industries. That project was completed on schedule, on budget, and is designed for 90% CO2 capture. But actually, it has demonstrated a capture rate of 92.4% CO2 capture. So it's actually capturing more CO2 than it was designed to capture. The technology developer said, while this is a first-of-a-kind application on a coal-fired power plant of this technology, the technology has been around for a while. But even so, they're still learning by doing that will happen by deploying more and more of these units. And the technology developer has said that the next-of-a-kind unit will be less expensive. So the next time they build this, Mitsubishi Heavy Industries has said that this could be 20% lower capital cost, for example. This project did have government support, being first of a kind. It got $190 million from the Department of Energy. So moving to the next slide, please. So in addition to the existing processes like these aqueous amines, the U.S. Department of Energy National Energy Technology Lab has been supporting the development of technologies with the aim of reducing the overall cost compared to what's available today. So on the right-hand side of the slide, you can see this is the DOE cost reduction. This is just for the CO2 capture. It doesn't include transport or storage. But these are generally per metric ton. In 2012, the DOE estimated that it would cost about $80 to capture each ton of CO2 from a coal-fired power plant. But over time, that has already gotten cheaper, and the DOE aims by 2030 to have that cost down to $30 per metric ton. And again, this is for post-combustion CO2 capture where you're retrofitting an existing power plant. You're adding it on the back end with all the other environmental equipment. So to drive down costs, DOE is looking at a lot of different options and novel technologies. And they're very similar to the aqueous amine process I talked about in the sense that the materials are reused over and over to capture CO2, but scientifically they're very different. So there's a lot of technologies that simply would not exist without the DOE investment in them, and some of those are actually already advancing towards the pilot scale, so being ready to be tested at the 10 or more megawatt scale. And so this program has had a lot of exciting developments over the years, and we are seeing these technologies make significant progress toward being ready for full-scale application. So please move on to the next slide. So the next slide, this is, so now we're moving off of post-combustion technology. So again, post-combustion was all the different types of technologies that could be applied to existing power plants, and we'll move on to pre-combustion. So pre-combustion CO2 capture is what you would apply if you were working with an integrated gasification combined cycle power plant, otherwise known as IGCC. The cost of the CO2 capture, just the CO2 capture step, is lower in this type of system because the CO2 concentration is higher, about 40% compared to about 12% or 5% for traditional coal or gas-fired flue gas, respectively. The challenge for the IGCC systems of CO2 capture is really on the gasification side. This is an all commercial technology, but the gasification step is quite expensive. And pre-combustion CO2s offer commercially, but even so, Department of Energy is still investing in technologies to try to drive down costs. And again, their focus is on things like solvents, membranes, and solid sorbents, just like they're looking at for post-combustion CO2 capture. And so move to the next slide, please. There's also another group of systems, you can call them advanced systems. These in general are new approaches to combustion or even new types of power plants. There's a few DOE programs advancing these technologies, such as the Coal First program and the Large Pilot program. And I've just listed a few examples here. So there's one technology called the Alum cycle. It's kind of hard to describe, but it is a supercritical CO2 cycle where basically under high pressure and a small amount of oxygen and lots of recycled CO2, then combustion can occur. And that's being advanced by a company called Net Power for natural gas. And they also have a coal cycle that does require gasification as well. So it's a new type of power plant where basically the power generation and the combustion are integrated, and they're happening at really unique conditions, and that is under development. There's also chemical looping, which is an approach to combusting fuel and oxygen, but using a carrier to release the oxygen in the boiler. And then there's another suite of technologies that I think are really promising that fit into the pressurized oxy-combustion category. And I just listed a couple here. One is stage pressurized oxy-combustion, another is flameless pressurized oxy-combustion. These are new combustion technologies that they combust fuel in CO2 and oxygen at high pressure. And so because you're using oxygen to do the combustion, you're going to have to do air separation on the front side. But you don't have to do post-combustion CO2 capture, because when you burn fuel in CO2 and oxygen, what you end up with is basically CO2, water, and a small amount of gas cleanup. So you don't have to have the post-combustion CO2 capture side. So what's so exciting about these pressurized oxy-combustion technologies is that they have high efficiency with integrated CO2 capture. Even though you have to do the air separation, they can still achieve high efficiencies, and they can also be flexible. So this is a really exciting class of technologies. And if we move to the next slide, I'll really briefly talk about one that we're working on here at the University of Wyoming. It's the flameless pressurized oxy-combustion power plant, and it's a new combustion technology. And you could do some retrofit, so you could place these at existing coal-fired power plant sites or natural gas sites to take advantage of coal preparation, turbines, electrical equipment, and more. It's a uniquely integrated combustion and carbon capture solution, which we believe will reduce overall costs. And if you can do anything with that CO2, sell it for enhanced oil recovery, sell it for something else, get a tax credit for storage, this is going to be we believe, compete very, very well with unabated dispatchable power generation. So this project that we're working on, if it's awarded phase 3 funding from the Department of Energy, it'll be constructed and operated on Black Hills Energy's Gillette Energy Complex, and we're really proud to have Black Hills and several other partners on this project. So one more slide, please. So, and I just want to give a quick plug for Wyoming. I think I just want to say that one thing I want you to know is that Wyoming is a great place. This type of research is alive and well in the state, and we have a lot of support. And I believe it's the place to do R&D, large-scale R&D on this type of work. And the reasons are simple. I mean, we have the mineral industry here maintains a very strong social license to operate. We have large coal production, largest coal mines in the world are here. We have a lot of infrastructure. We also have Class 6 well primacy for CO2 storage wells, very supportive state and local governments and proactive communities. So with that, I am done with my presentation, and I see that Jason is on board, on deck, and I will hand it over to you, Jason.
All right, thanks. Hopefully everyone can hear me, but yeah, kind of gonna take the next step moving forward, talking about carbon utilization, and you know, both Holly, mine, and Scott's presentations do kind of really weave together very nicely. So next page, please. All right, and I'm going to start talking about the Integrated Test Center, kind of a little bit of a plug for we're really one of the main projects that we're involved with. That is a test platform to commercialize and scale up both the types of carbon capture technologies that Holly just spoke about, as well as carbon utilization, because clearly you do need to do something with that CO2 after you've captured it. The Wyoming is really unique just due to this facility that it has. It's the only facility of its kind in the Western Hemisphere. It's supplied with about 20 megawatts equivalency of flue gas from the Dry Fork Power Station. And why that's really important is most utilities would need to see a technology demonstrated, you know, at least 10 to 20 megawatt in scale before they felt comfortable taking it to that next level and doing a full-scale commercial project. You know, when you look at most laboratories, you know, you're dealing with a couple kilowatts in size. You know, if you go to the National Carbon Capture Center in Wilsonville, Alabama, you know, you can maybe go up to a megawatt, megawatt and a half. So the ITC really is that platform to do that demonstration pilot scale that is needed to take that jump to commercial. The facility itself is very bare bones, which provides for a lot of really great opportunities with for flexibility and scale up. You know, we're not inside a building or have any constraints really regarding, you know, height. So if you have a technology such as an Amines system that would need a tower, you can go really as high as you need to go. Or if you need more of a modular system that's kind of short and spread out, we've got area for that as well. So next slide, please. So who are the partners in this? You know, it's the state of Wyoming. Basin Electric is the host of the facility. Tri-State is another utility. Both Basin and Tri-State are rural electric transmission and generation cooperatives. They provided $1 million in cash, or excuse me, $5 million in cash cost share. Another $1 million from the National Rural Electric Cooperatives. I see I've got an old slide, but the Infrastructure Authority, which now is part of the Energy Authority, is the managing entity. And then our other two investor-owned utilities within the state, Black Hills and Rocky Mountain Power, provided some technical expertise and other types of in-kind contributions. So it's a really unique sort of public-private partnership to find these sort of technologies. Next slide. So again, you know, where's the uniqueness of the ITC? It's right there in the middle. If you look at sort of the evolution of these technologies as they go from an idea to actually commercial, there's several scale-up opportunities. So You know, the ITC does provide a really unique sort of niche right there in the middle to be able to show what we need to do. Next slide. So again, you know, these scale ups, starting on the left from a bench scale to a skid to a demonstration to, you know, full scale commercial, and the one on the far right there is a picture of the Petra plant. So, you know, you start small and scale up, but you need places to do this. Next slide, please. And so, you know, I won't go over or I guess duplicate what Holly had talked about, but really the first phase is capturing the carbon. Next slide. And here are a lot of different types of technologies that do exist out there: pre-combustion, oxy-combustion, post-combustion. Again, won't go into that in great detail, but just other to say that there are a lot of different ways out there to capture the CO2. Certainly some are much more commercially viable or ready than others. Next slide, please. So that brings us to this next stage here. What do we do with the CO2? You know, Scott will talk a little bit about geologic sequestration. You know, for permanent storage, you could almost say enhanced oil recovery is another form of geologic sequestration. Won't talk a lot about that here. I think it's pretty well understood what that is. But I'm mostly going to talk about CO2 conversion. You know, what can you do to take that carbon dioxide and potentially convert that into other products that have a value? Next slide. So you really, and it's probably really dangerous of me to try to do a chemistry explanation, you know, following Holly, who actually does have a doctorate in chemical engineering, but I'll do my best here and try not to make a fool of myself. But, you know, really what we're talking about is carbon. You know, carbon is all around us. It's present in living organisms, diamonds, graphite. Humans, we're all, you know, all carbon-based life forms. And, you know, most importantly, or what we folks tend to focus a lot on, it's part of fossil energy. It's hydrocarbons. It's right there in the name. So next slide, please. So, you know, what is the issue then? You know, and that is the fact that when hydrocarbons are burned, the hydrogen part is consumed and water and CO2 are formed. You know, water's not a big issue. You know, we use that, it's part of everything, but the issue there is the carbon dioxide. And really what is interesting, or really a difficult part of that, is if you look at that carbon dioxide molecule, you'll see two bonds between the carbon and the oxygen. And the problem with carbon dioxide sort of utilization is that those double bonds are very strong, meaning it takes a lot of energy to break them apart and do something else with them. So, you know, CO2 is a very stable molecule, which is great for some aspects. Other aspects make it a little bit more difficult. Next slide, please. But in theory, you know, the captured CO2 can be utilized in a lot of different ways. You know, if you're able to sort of either break down those bonds through a chemical process or utilize them in sort of a natural sort of photosynthesis types of process. You know, one way is converting or using the CO2 to feed algae that can then be processed into oils and you know, fuels, those types of things. Chemical reactions to make a fertilizer, feedstocks, you know, mineralizing the CO2 into products such as, you know, building materials, concrete, cements, things like that. So from a chemical standpoint, there are a lot of different things that the CO2 can be used for in both its presence form or in breaking it apart. Next slide, please. And that sort of leads us to a really neat partnership that we have with the XPRIZE Foundation at the Integrated Test Center. And XPRIZE, I don't know how many people are familiar with it, but they are an organization that funds these really neat engineering competitions to solve kind of major challenges, societal challenges. They've done things, everything from healthcare to clean water. The one that they're probably most known for is SpaceX. And so that sort of private space travel industry really was based off of an XPRIZE competition that was held in the late 90s. And so several years ago, XPRIZE partnered with NRG, a utility based in Houston, and COSIA, which is the Canadian Oil Sands Association, to fund the NRG COSIA Carbon XPRIZE. And the whole goal of that project was to award $20 million in total prize competition to the teams that are best able to capture that CO2 and then convert it into some sort of marketable project. So, you know, it's really based on both the science and the economics. There were 3 rounds to the competition. I believe originally there were like 46 teams from 8 countries. It had scaled down through several rounds, and now we're in the final round 3. And we have teams at a natural gas plant in Alberta, as well as teams at the ITC working on flue gas to discover ways to utilize that carbon and CO2. So next slide, please. And so here are the 5 teams that made it to the final round of the coal tract. Right now we have UCLA, the UCLA team on site, and Dimensional as well, working on their projects. Unfortunately, COVID created some very unique challenges and flat out made it impossible for the foreign teams to get visas and travel into the US. So, you know, XPRIZE has worked with them to find an opportunity for them to perhaps test in their home countries. We have teams from India, the UK, and China that are a part of it as well. So some really unique things that are happening out there and ways that they're looking at using the CO2. Next slide. So another partnership that we have in utilization is with JCOAL, which is Japan Coal Energy Center, which is sort of a Japanese trade association focused on you know, the coal industry within Japan, both, you know, making sure that they have enough to make electricity, but also dealing with sort of some of the vendors such as Mitsubishi, Hitachi, Kawasaki that make parts to power plants and emission control technologies and things like that. And then the other partner in this is GreenOre. And GreenOre is a carbon utilization company that was spun off of a technology developed at Columbia University. And so what you can see below is a picture of a pilot plant in China that is using CO2 from a steel manufacturing facility and a calcium input from the steel slag to create carbonates that could be used for concrete and aggregates and things like that. And the one thing that's unique about Powder River Basin coal is that the coal is high in calcium. So we've partnered with JCOAL and GreenOre to see if we could use fly ash from power plants and CO2 to basically replicate the technology. And so last year we signed an MOU with everyone. There have been some trips back and forth before COVID hit, and hopefully later this year we can start some small scale testing to see, you know, if CO2 from a power plant plus the fly ash could mitigate both carbon dioxide, but also make a marketable product. Next slide, please. All right, and that there is my the contact information. And I guess looking again, seeing that I haven't updated the slide, my apologies. Should be Energy Authority, and I'm the deputy director there. And with that, I will turn it over to Scott.
All right, good morning, everybody, and thank you, Jason. Thank you, Holly. I will be the third leg of this race, and I will be talking about the storage component of carbon capture and storage. So next slide, please. I just want to, a few of the examples in this presentation come from a sponsored project from Department of Energy. So I just want everybody to know that they are not responsible for what I say. So next slide, please. Today, I thought I would give an update on what the Carbon Storage Assurance Facility Enterprise Program is, or CarbonSAFE, through the Department of Energy. Through this program, it seems to be driving nearly all of the research towards commercialization for carbon storage. So to do that, I'd like to just give you a background on that program, and then give you a primer on CO2 storage using the language from our Class 6 underground injection control program, and weave in examples from the Wyoming CarbonSAFE project to show you. So next slide, please. So let me start with background on what the CarbonSAFE program is. This is the flagship program for CO2 storage through Department of Energy. There is a link on the bottom of this slide if you want more information. Please click that link. But it's focused on moving towards commercialization of carbon storage at a commercial scale, so 50 million tons. It may take 25 or 30 years to accumulate that 50 million tons, but they are looking at developing commercial scale carbon capture and storage complexes. And there's several across the US that are in this program. There's 5 currently. And as Wyoming is a recipient of this program, I have to give my hands off to Department of Energy for having the forethought of putting this program together. It's an aggressive schedule. It started really in 2017, and it's moving towards having a large-scale, fully operational commercial facility sometime circa 2025. And they're looking at getting there through a 4-stage program. So recently, we just moved into phase 3. Phase 3, if you can see there on the right, will be a three-year program. It will include permitting Class 6 wells for injection. It'll include the final characterization and the NEPA analysis needed to move forward on these projects. And for the first time, we'll be integrating with the capture technologies that are working at this site. So here at the end of phase 3, in just 3 short years, we could have several projects on the cusp of moving into commercial operation. Now, of course, phase 4 is up to future appropriations and a bunch of other factors, but we could be there in 2025. Next slide, please. Several of the examples I'm going to show today are from Wyoming CarbonSAFE, so I just wanted to share a couple of slides so that you have the background here on what Wyoming CarbonSAFE is. It is operating at Dry Fork Power Station, the same place as the Integrated Test Center. You can see Dry Fork Power Station in the back of this picture on the right. That's the well that was drilled recently to characterize the subsurface below the power plant. But really, we are looking at safely storing commercial quantities of CO2. We're trying to understand what the risks are, what the costs are, what the policy drivers need to be in order to move this project forward. And really, and we're also working with the local folks to make sure that we have the social license to operate this project. Next slide, please. One more plug for Dry Fork Station, and Jason just went through it thoroughly, but it is one of the newest, cleanest coal-fired power plants in the US. It emits about 3.3 million tons of CO2 per year, and it has a long operating lifespan ahead of it. I think we're looking at about 2070 for the life of this plant. So this is not a plant that's on the chopping block or one that's going to be closing here in the near future. So having a carbon management plan or an operation plan for this plant makes a lot of sense to keep it going way out into the future. Next slide, please. So let me give you just a brief primer on carbon storage. Now this is a very simple diagram here on the right. It's a cartoon that we use for public outreach around our project. It was actually developed by our project partners at the EERC. But there's a few myths I would like to just go through with carbon capture and store with the storage component that I continue to hear over and over again. So I'd like to just break those through and then use the terminology from the Class 6 wells so everybody here understands what we're talking about. So one myth that we commonly see is when CO2 is injected in the subsurface at temperature and pressure, it is a supercritical fluid, so a dense phase. It's no longer a gas at that point. So when it's in the subsurface, it behaves just like a fluid. It's a buoyant fluid, so it's a little more buoyant than water. But when you inject CO2 as a fluid, it displaces the salt water that's down in formation and takes its place. I do want to give one little plug for CO2 enhanced oil recovery. I think, just as Jason mentioned, I think most people understand what that is. But it does help us get to about another 30 or 60% oil recovery from these reservoirs. And when you're doing it, you have associated storage too. So it's a great utilization tactic for CO2. But as we go forward, as we start looking at capturing carbon dioxide from power plants, as we look at direct air capture, or in the future, or if it's from blue hydrogen production, we need lots and lots of CO2 storage sites available in order to store that CO2. We're talking on the billions of tons. The room is just not there for enhanced oil recovery to take all of that CO2. So we really need to step into the next realm, which is saline aquifer storage. Next slide, please. So stealing the language from the Class 6 UIC program, Class 6 wells are the well that's used to inject CO2 into the subsurface. I just want to talk about a few components of this program. So quoting from the rules here, you need a suitable geologic system with an injection zone, a confining zone. I'll also talk about what the area of review is. And what else are we going to talk about? Site characterization. What's neat about the CarbonSAFE program is it really takes all of these projects through the first 3 bullets of the UIC program. So next slide, please. What is a suitable geologic system? So using an example from the Wyoming CarbonSAFE project, on the left, you have a stratigraphic chart. If you've ever been subject to a geology chart, you're always forced to look at one of these. So how to read this chart, you can picture yourself standing on the surface at the very top of that chart and looking down. If you could peer down through the rocks all the way to the basement rocks or the granite below, you have a stratigraphic section stacked on top that's all sedimentary rocks. So this chart shows you each geologic formation as you go down through the stratigraphic column beneath your feet. When you're looking for a suitable geologic system for CO2 storage, you have to be below what's called the lowest USDW, so the United States Drinking Water Aquifer. In this case, the lowest USDW is the Fox Hills Sandstone on that left chart, so very, very shallow. And generally, when you're looking at these systems, you go below any oil and gas reservoirs that are in the area. So that way that you don't have oil and gas wells then shooting through your CO2 storage target currently or in the future. So in this project here, we're going all the way down to the bottom of that stratigraphic column, which is the Menalusa. We know we are below the USDWs. We know we are below the oil and gas production in the area. In the middle chart, you can see a geophysical well log. This is what we use to characterize those formations directly below your feet. So I've cut off the section there that tells us about the Menalusa formation, and we've colored those sandstones yellow. Those are our injection zones, as the UIC permit would refer to. So we've got 4 different injection zones within one formation at the bottom of the stratigraphic column. Now on top of that, you can see we've got a bunch of shale. That would be our confining zone. And in fact, we have one big, thick salt zone right up there with the goose egg formation that's full of anhydrite. So that is the sealing part of the formation that sits on top of your reservoir zone. On the right, I've just brought up some pictures so you can see what these rocks actually look like in outcrop. So they're not a big black box in the subsurface. They actually have different facies within them, but you can see them there on the cliff face on the right. Next slide, please. So let's look a little bit closer at our injection zone. So on the left, you can see the rock that we took out of the hole. This is about a 3-inch scale there. So one myth that I think sometimes is misunderstood is where the CO2 is being stored when we put it down there. So if you go to the picture in the middle and then all the way to the picture on the right, these are just microscope images of that rock that came out of the CO2 storage complex. The blue colored between those grains, that's the pore space. So that's the area between the grains that we are looking for, exploring for, so that we can put CO2 into them. Permeability is the other term that we often use, and that tells us how interconnected those grains are. So just like if you remember back on Saturday mornings when the maize was on the back of the cereal box, you can take your pen and trace between those pore spaces. You can see, you can interconnect most of them. Some of them you can't. So what we're looking for in the reservoir is good porosity, so good pore space, and good connectability between those grains and the permeability. So next slide, please. I'd also like to talk a little bit about what the confining zone is. And from a public perspective, I always get the question of, how do you know it's going to stay down there if you put it down there? So we do a lot of work on our confining zones, our seals, our traps, and looking at what the lifetime of that CO2 will be in the subsurface. So let me start on the left. This shows our reservoir rock from the previous slide. We've got a 500 nanometer scale bar on the top left of that, so we're looking at it pretty close. We've got lots of pore space in that rock. Directly above it at the same scale is the seal for that rock. And so you can see that there's hardly any pore space in that seal. So I usually use the analog of pouring coffee into a ceramic mug, where your coffee cup is your reservoir. You can pour the coffee in there. It's held in there because that ceramic mug has very, very little porosity and permeability. So it's kind of the same concept here, where you have a buoyant CO2 fluid that's pushing up against that seal, but it can't go anywhere. So it's held in there. But we also need to know that that seal is laterally contiguous. It can't just be in one spot and not in another. So what we do on one of these storage complexes is not only do we drill a well, but we'll also shoot a 3D seismic survey, and that will give us resolution on these rocks moving away from the well. And we can start looking at what the traps are. So in the middle, I'm showing just 2 traps. These are conventional to oil and gas, but it's the same thing for CO2 storage. You can have a structural trap where you have a little anticline or a little bulge in the subsurface where you can put a buoyant fluid and then it'll be sealed as that seal rock wraps around it. Or you can simply have a stratigraphic trap, and that's what we see in a lot of these carbon capture and storage complex, where you have a nice reservoir rock that directly lies underneath a seal. So when you put the CO2 down, it's held for geologic timescales. On the right is our mineralization chart. You can see that when you physically put CO2 down first, it's held there physically through structural trapping. But as it sits there longer, it begins to dissolve into the brine, it begins to move into the pores away, it's trapped through capillary pressure. So the longer the CO2 sits, the more safer and stabilized it becomes. Next slide, please. The other important concept in the EPA's underground injection control document is the area of review. Calculating the area of review is not just the plume of the carbon dioxide that's down in the subsurface. We also have to have an understanding of all the displaced brine that the CO2 took the place of. So on this little small figure on the right, you can see 4 points. These are simulated wells, and this is an older diagram, but it's great for an example. So you can see our 4 simulated wells as dots there around Dry Fork Station. Those dotted lines going out around each one of those well bores demonstrates where we think the plume might lie. And it's statistical, so we have a 90th percentile, 50th, and a 10% percentile. But the plume itself usually goes out from around the wellbore maybe a mile and a half. The displaced brine, on the other hand, is more like on a 5-mile scale. So we need to understand both where the CO2 goes and where the brine is being displaced to. Next slide, please. The last concept I wanted to talk about today is geologic heterogeneity. It's not just a black storage tank or black box or a storage tank in the subsurface. The reservoirs differ quite a bit. So each one of these diagrams here, the one on the left is showing the porosity distribution across one formation below Dry Fork Station, and the one on the right is showing the permeability distribution across Dry Fork Station, or across the formation. The yellow in both figures shows us where we've got good porosity and permeability, and the blue colors or the cold colors show us where it's not so good. So what we're doing in this simulation is putting CO2 in, and we want to see how it can move from across formation and what those plumes look like. Next slide, please. So this simulation here, we're dropping one well right in one of those good zones, and we're starting to pump CO2 into it. So right away, what we're seeing is it fills up that compartment that was kind of a good zone, and it goes through a little tiny bottleneck, and then it goes into the next good zone. So it's not simply just a plume that goes out equally away from the wellbore across formation. So we really need to understand geologic heterogeneity if we're going to understand where those plumes might migrate and where those pressure plumes or area of review might be. Next slide, please. So on this slide here, we wanted to demonstrate that what happens to the CO2 plume after you stop injecting. So the first slide showed us injection for 50 years, and then we cut it off, and then we let the model sit and run for another 50 years to see what might happen to that CO2 plume. So in this case, you can see it looks very, very similar to where it was on the day we stopped injecting. So once the pressure buildup begins to stop being built up through injection, it starts to come back down and it stabilizes. So you can see this plume, even after 50 years post-injection, it's just kind of sitting right where we put it. So that's a good sign. So next slide, please. So what's next for Wyoming CarbonSAFE? And really what's next for all of the CarbonSAFE projects? And in this next phase, like I said, we're going to be finalizing the geologic characterization, going through the Class 6 permitting process, getting these projects dialed up and ready for commercial operation, and finalizing the NEPA and environmental analysis. So next slide, please. And I think I need to leave time for questions. So let me stop there.
Excellent. Thank you all so much for these really fascinating presentations and wonderful explanations. We do have a few questions that have come in. We will ask those in just a moment, and I want to remind folks that you are most welcome to continue to drop questions into the questions box. We will get them to our speakers. And also, you may raise your hand and we can unmute you. The first question is for Holly. Holly, we had somebody ask, how has capture integration impacted the availability and capacity factor of the power generation at the NRG project that you mentioned?
Thank you. Yeah, thanks for that question. So I don't have direct knowledge of how it's impacted the capacity factor, but I do think it's really important to understand what happened to Petra Nova. They did not, they are not accepting, the Petra Nova project, the CO2 capture part, is not accepting the entire flue gas stream. So that is accepting a slip stream of 240 megawatts equivalent, 240 megawatts electrical. So the rest of the flue gas does not go through the CO2 capture system. So that allows the whole power plant to be able to ramp down to a level something above 240 megawatts electrical before it would have any impact on the CO2 capture system. So they are operated a little bit independently, but I don't know what it's done to the availability of that power plant. I haven't seen that information.
Okay, thanks. We had a related question about Petra Nova's offtake being shut down last month or 2 months ago. Do you have any knowledge about the situation there?
Yeah, I think this is a really good point. So you've seen probably some articles talking about how the Petra Nova project is not operational at this point. And I think it's really important we address that on this call, because that is not indicative of the CO2 capture system. So the question actually asked, how is it a positive example? And first of all, it is a first of a kind project for Mitsubishi Heavy Industries on coal-fired power plant. It was completed on schedule, on budget. It has a higher CO2 capture rate than it was even designed to capture. But what I want to explain is, why is that plant shut down right now if it's so great, right? That's the question. And what I think you need to understand is that project, that CO2 from Petra Nova, is directed towards one specific oil field that's doing enhanced oil recovery. So that specific oil field right now at current oil prices is not economical. The project is not shut down because of the CO2 capture system. It's shut down because the oil production from that particular oil field is not competitive. So they can't accept the CO2, they can't produce. And I think it really speaks to the need for, if we're going to build a robust CCUS industry in this country, you can't have just one plant connected to one oil field. We need to have some interconnection, and we also need the option for storage. So for power plants that could use the 45Q tax credit that do CO2 capture retrofit, right now, they would probably, if they had the option between enhanced oil recovery and doing saline storage, they would probably opt for CO2 storage and saline aquifers and accept a tax credit rather than payment and a tax credit for enhanced oil recovery. So it is complicated, but you can't judge that the Petra Nova project simply because the oil field that it's that it sends CO2 to is not economical right now under, pandemic and oil price war conditions.
Thank you very much, Holly. That is a really important point. Scott, we got a couple questions in for you. One
Sure.
is, what's the biggest challenge in the mineralization method?
So there's, I wouldn't say there's challenge. It happens, it gets there. I think it has to do with time, and it has to do with rock type, and it has to do with formation brine chemistries. So certain rock types mineralize CO2 much faster than others. It's just a matter of understanding what's down there and how long it takes to get to develop the carbonates.
Great, thank you. And we also got a separate question saying, apologies if this is a basic question, but do we have function of pore space and size to understand the ability to keep CO2 gas trapped? Is it a function of pore space and size? I believe you may have addressed that.
Yeah, so what traps CO2 is our seals, and it does have to do with pore space and size, but those seals will keep the CO2 trapped in the reservoir rock.
Great, thank you. Always good to have those clarification questions answered. Let's see, we got another one, Scott, for you, saying the site for storage you displayed in a graph of the country, the sites for storage that you displayed, are these potential sites identified or have they been secured as deposit sites? So the graph that you had, are they actually secured sites or potential sites?
So the graph that was shown is illustrating the DOE carbon storage program activity. So it shows those hubs that are working towards CO2 storage in the CarbonSAFE program, but it also shows the carbon capture facilities that are in the CarbonSAFE program. So those are the hubs in the areas of the country that are pushing it forward.
Okay, I'm going to ask one last question. We need to leave ourselves 1 minute for announcements. The last question was for any of the speakers. During the commercial upscaling across the U.S., who do you anticipate would execute the storage site studies and actual injections? Oil companies, startups, or others?
Is that one to me?
The future.
I think
I'll take it, but I'll start and you guys can weigh in. I mean, I think oil companies, surely they have a lot of subsurface knowledge, and I would just point to one in particular. There are several that are very engaged in this space, but Occidental Petroleum has already announced projects where they would do saline storage. So I think that process has already started. I don't know, Scott and Jason, if you have other additions.
I agree. I think it depends. I think the oil companies have the expertise to do it. So yes, it'll be startups and oil companies, but it'll probably happen outside the fence of utilities.
Great. Thank you all so much for your presentations and for your willingness to go through the questions. We did get a few more questions, but I'm afraid we've run out of time. I will send those to you separately. Jasmine, could you go to the last slides for announcements, please? We just wanted to make sure folks were aware of our upcoming webinars in this series. There are 4 more to go. Next week's is on financial incentives and investment efforts. And then we have a 2-part project update around domestic and international CCUS development efforts. And finally, regulatory considerations and policy recommendations. If you signed up for today's webinar, you are automatically signed up for the additional webinars. So we hope that we will see you there. And I will turn it over for one last announcement to Kip. I'm sorry. Yes, I'll do that one. The fall 2020 joint CREPC-WIRAD meeting webinar series is going to be happening later in October and November, and you are certainly invited to join that one as well. You can go to westernenergyboard.org for those. And that concludes our webinar for today. The webinar next week will feature Michael Nassy from Jackson Walker LLP and Shannon Angelski from Carbon Utilization Research Council. Thank you again to all of our speakers, and thank you to everyone for joining us today.
Thanks.
Thank you. Nice job, Scott.